Remember, you have the number of members in your ring, crown, number of oxygens in your ring, ether. And so sometimes he might not put the ether at the end. That's why I wrote blank, crown, blank. Always remember the bigger number is going to be first, smaller number will be second. And on this first one, what I had done is go through and count all of the members of the ring just to show you that the answer is 12. But the easy way to do that is to multiply the number of oxygens by 3, and you get the number of members in your ring. So for example, 1, 2, 3, 4 oxygens times 3 would be 12. So the answer is 12 crown 4 ether. The answer to the other two is right here on this page, and I covered it in the video, so you guys can watch that if you have any questions. And someone said, why multiply by 3? It just kind of works, and I think it's because of the way that the ether is structured. So, like, you can almost think of it as 1 oxygen and 2 carbons being like 1 unit, almost. If that makes sense. If not, just remember it, because it's just one of those things. That probably wasn't a great answer, I'm sorry, but it was just a trick someone taught me once and it stuck. And I feel a little bit under the weather today, so I apologize if I sound like I'm dying. I'm fine, I don't have COVID or anything. Any questions about this before we move on to new stuff? No? Okay, cool. So this is actually where stuff gets fun, and I'm very excited because Chapter 9 and the beginning of Chapter 11 are really sort of boring. And this is when things get interesting. So we actually covered a little bit of this last week as well, I believe. I don't know if we finished, but I'm going to ask you guys to lead me through this first reaction. So what functional group is this right here? Alcohol, sweet. And if we react our alcohol with something that has a negative charge, to the people who were here on Friday, anything with a negative charge can be a what or a what? A base or a nucleophile. Awesome. And you guys had already beat me to it and answered this in the chat, but you're actually going to make the conjugate base, and it is going to become the alkoxide. And the reason for that, just to clarify, is that the OH minus will attack the hydrogen and steal it and give the electrons to the oxygen. Now here we have a carbon chain with an X group. Someone tell me what X stands for. Halogen. Awesome. And then if you have your mic on, pretty please turn it off because I'm getting distracted. So we can have bromine, chlorine, iodine, any of those things. So this is going to be called an alkyl for the alkane. Wow, that was awesome. I don't know why I did that. It is an alkyl halide. So when we react an alkoxide with the alkyl halide, the negative charge will attack this carbon and kick off the leaving group. So this acted as a what? Nucleophile or a base? Yes, nucleophile. Sorry guys, give me 1 second. Okay, I think I fixed the audio issue. But yes, it acts like a nucleophile, it attacks the carbon, and we make this functional group. What is this? An ether, sweet. Cool. And this is the Williamson ether synthesis. And we can actually do an intramolecular version of this synthesis. And the only difference between these is that in the intermolecular version, the nucleophile and the leaving group are on 2 separate chains. Versus in the intramolecular one, our leaving group and our nucleophile are on the same carbon chain. So if we react it with a base, the base will take a hydrogen again, and we make the alkoxide. And let's just say the halogen here is chlorine, just because I said so. Now the oxygen can attack this carbon and kick off the leaving group, just like we did before. But now we're actually going to make a ring, and I'm going to draw it in two different ways for you guys. So first I'm going to draw it kind of coming out of the plane. So the ring has two wedged arrows, or not arrows, it has two wedged lines. And the reason for that is this oxygen is wedged, and in order to kick off the leaving group, it has to be opposite to it. And so it has to come from behind and attack from the backside, and that's why we can draw it out as both being wedged. However, the way you'll usually see it written is having the epoxide on the plane, or the ring on the plane. And so how we keep our stereochemistry is we will make these groups, the two methyls, trans to one another, because on the linear chain, they're pointing opposite directions. So we can just do bam and bam. So they're trans. So what did we create here? What functional group? Come on, guys. A cyclic ether. Awesome. Now that answer is 100% correct, but what else could... Oh, you guys already beat me to it. We can also call this an epoxide. And an epoxide is special because it is a cyclic ether. But what is something special about an epoxide? My people who were here Friday, you guys should know. Yes, it has 3 members. It's very, very reactive. And I gave one more fun fact, but I don't really expect you guys to remember that. The epoxide has something called banana bonds, which I just find funny, and Dr. West usually talks about it. So there's so much ring strain that these bonds are going to get really gross and bent like this, which makes it super, super reactive, and that contributes to some of the stuff we're going to talk about in a little bit. Now, the reason I pointed out that this is an epoxide is so I can kind of drill the point that epoxides are a type of cyclic ether. So every time you have an epoxide, it is an ether. But just because you have a cyclic ether does not mean you necessarily have an epoxide. That's something that people get tripped up on sometimes. So since I said that, we're going to do another example of this reaction. And I'm sorry about Bear. So let's say we react this with NaOH again. So we have a base. We're going to steal that hydrogen. Nothing new there. So we have our O- and our Cl. So we should already know at this point that this is going to go ahead and attack and kick off the leaving group. And I know my arrow is kind of ugly, but it's whatevs. So at this point, I need you guys to be very careful in counting your carbons. So we're going to count this as 1, just because I said so. You could have started the other way around. 2, 3, and we know the oxygen has to go inside the ring, so I'm going to count that as number 4, and we're going to draw it this way. And I always like to start with my oxygens just because it's easier to keep track. And then we have 1, 2, 3 carbons, and let's number those 1, 2, 3, and 4. And we have 2 methyl groups as our substituents, and they will be on number 1 and number 3. And the reason I draw this is, again, to drill home that point that our product here is a cyclic ether, but it is not an epoxide. someone said my screen froze, which is super awesome. We love that. So it's loading. Let's see if it'll work now. Did it pop back up for you guys? Yes? Okay, awesome. You gotta love technology. Okay. So that's pretty much it for the Williamson ether synthesis. I'll zoom out so you guys can take a screenshot or whatever. So the intermolecular Williamson ether is when two separate molecules interact with one another and form an ether that is linear. And the intramolecular is when the nucleophile and the leaving group are on the same carbon chain. And we always end up making a cyclic ether. Sometimes we will make an epoxide if we have the right number of carbons. And someone said, why did I number the chain like this? Literally just because I wanted to. This is completely arbitrary. I just like to I like to number the carbons that are going to be inside the ring. And it helps me make sure that my ring at the end is the right size. Does that make sense? I hope. Okay. So, any questions about this before we move on? And someone asked, what is always required to make an epoxide? We're actually going to go over a couple other things that can make an epoxide. If you still want me to go over this after, let me know. And yes, let me just explain inter versus intramolecular one more time. So intermolecular is just this reaction. And intermolecular means that two different molecules are going to interact with one another. And that's going to be the alkoxide, which is the nucleophile, and the alkyl halide, which has our leaving group. Versus intramolecular means that the leaving group and the nucleophile are on the same carbon chain, and that will give us a ring as our final product. And I'll leave this for like one more second while I sip. And cool. So now that we made our ethers, we're going to break them naturally. That's the order of things. So when we're breaking our cyclic ether, someone who was here Friday, or if you just know the answer, when can ethers be cleaved? In acid or in base? Acid, yay. And that means that they are stable in base. Alrighty. And then we have the order of reactivity, and I'm going to put a little asterisk by reactivity. And right here, I'm just going to say, what I mean by reactivity is the order that the nucleophile will prefer to attack on the chain. So the order of preference the nucleophile has when attacking. And I'll explain what I mean by that in the next example, but I just want to write that down for you guys. So, I'm going to give you a fun way to remember this, and it's going to sound weird at first. I hope it makes you laugh, but you'll remember it. So, acids are a pain in the ass because they don't go in regular numerical order. And we know that regular cyclic ethers are only cleaved in acid. And since they are a pain in the ass, the order is tertiary, primary, secondary. And I'll explain what I mean by that in just one second. But are there any questions about what I have so far? So someone said, what is a cleavage? So cleavage is basically when you break bonds and you break it apart. In this case, we're going to open up the ring. Alrighty, so I'm going to zoom in. I'll zoom back out at the end, so don't panic. But also I realize it's really dark in here, but whatever. So HBr is an acid, and the first step of this cleavage will actually be the activation step, and Dr. West loves to talk about that step. So we're going to take that hydrogen, give the electrons from the bond to the bromine. And the reason we say that this has been activated is because we have a plus charge on our oxygen. So why would the plus charge make it activated? What do you guys think? Someone said so that bromine can come in. Yes. It's able to be deprotonated. That's also true. Someone said it makes it acidic. That's also true. But someone said that it makes it a good leaving group. And all of those things you guys said were true. But the reason we want to make it protonated is because it becomes a better leaving group. And so what do we mean by leaving group? Well, when our Br minus or bromide comes in, it has a negative charge. And now I want you to tell me this carbon is what? Primary, secondary, or tertiary? Ooh, okay, so I got some people saying secondary and some people saying tertiary, which is exactly the split I wanted to get. So this carbon, oh no. Okay, so this carbon, oh my gosh, sorry. This carbon is attached to 2 carbons and an alcohol, an alcohol. This oxygen doesn't count towards primary, secondary, or tertiary. So this carbon is actually only attached to 2 groups, making it secondary. But I'm glad you guys got it wrong here and not on the exam. That's what we're here for. So what about this carbon? Primary, secondary, or tertiary? Primary. Awesome. Okay. Don't mind me while I change the color of that. So acids are a pain in the ass, and that means between secondary and primary, what are they going to choose? Primary, exactly. Bam. And when we attack on the primary side, that means we are going to break this bond. And we are going to open up the epoxide that way. And now we're going to count our carbons again. Make sure we have that in line. So I'm going to start here just because. So 1, 2, 3, 4, 5, 6. So I'm going to draw a 6 carbon chain. 1, 2, 3, 4, 5, 6. And we'll call this 1 and we'll call this 6. So attached to carbon 1, we have our bromine, which was our nucleophile. And off of carbon number 5, we have our OH group. So I'll go through and explain it really quickly one more time. So in the first step, we activated our oxygen and made it OH+. And then we had our Br-, which will act like a nucleophile. And between the secondary position and the primary position, it will choose to attack primary because it was an acid and it's a pain in the ass. And then once we break open the chain, since we attacked this position, it will open towards the secondary side. So our bromine will end up on carbon 1 and our OH will end up on carbon 5. Any questions?
How did you know, like, if it was like primary or secondary? Like, how did
Great
you know
question. Okay, so when we're looking at carbons, I'll highlight it in pink, the one I'm talking about. So the carbon in pink, we are going to look at how many carbons it's attached to. So it's attached to 1, 2. Oxygen doesn't count, so it is secondary. Versus the one in green is attached to 1 carbon, and that's it. So this is primary. If it was something like this, actually, let's just do tertiary for now. So if we had something that looks like so, the pink carbon is attached to 1, 2, 3 other carbons, so it is tertiary. Make sense? Oh, the screen is lagging. Of course it is. So I'll explain this one more time. So the pink carbon is attached to 1, 2, 3 other carbons, and that's why it is tertiary. And then people in the chat were asking, so if you were to break it on the secondary side, like hypothetically speaking, then yes, it would open towards the primary. And the reason we preferred side primary over the secondary side is because acids prefer primary to secondary. That has to do with steric and electronic effects, but for the purposes of this class, as long as you know the order, you're completely okay. Okay, the only difference between these two reactions is that the second one has excess written underneath it, and I'm just going to go ahead and give this to you guys because when I was in this class, one of my really close friends got this question wrong on the exam because it said XS and she thought it meant extra small. It does not. XS and XS mean the same thing. Okay. In the first step, we're actually going to make the same product, so I'm just going to go ahead and duplicate it, right? We did the exact same thing. But now at this point, we have excess HBr. So we have another molecule of HBr, and now I'm going to write that in red. So what do you think the first step is going to be? You guys can either do it in the chat or unmute. And there's no wrong answer. Well, technically there's a right and wrong answer, but I want to hear whatever. Someone said protonation, exactly. So we're going to activate the oxygen again. So it's going to, bam, take that hydrogen. And I'm lazy, so I'm just going to duplicate that again instead of redrawing it. So now instead of just an alcohol, we have H2O plus. And so now this became a better leaving group. And our Br minus can go ahead and attack that carbon and kick off the leaving group. So we end up with excuse me, it was a weird color. Instead of an OH, we now end with 2 BRs. And someone said, are these through SN2 mechanisms? I believe he describes them as SN2-like. So that's what I like to call them. And as far as inversion goes, yes, you would, but it's not a big deal in this class. He's not going to ask you to specify the stereochemistry at this carbon. But yeah, theoretically, if he were to ask, you would see inversion. So guys, I know we did more reaction mechanisms, and Orgo 1 has scarred you for life, so you probably hate reaction mechanisms. But I promise, in Orgo 2, they're not that bad. And ask me any questions if you want in the chat. I'm going to spend a minute letting you guys look at this and ask questions. Someone said, how do you know which way to break this? I will go ahead and show you another example. So I'm going to go to a new page. If it will let me make a new page, that would be awesome. Okay. That's a really ugly benzene ring, but you guys, or it's not a benzene, cyclohexane. All right, so I gave you 3 examples here. So first thing I want you guys to do is let me know for this first example right here, the carbon that I have pointed to in pink, what do you guys think it is? Primary, secondary, or tertiary? Tertiary, exactly. And the reason why we call that tertiary is because it is attached to 1, 2, 3 carbon groups. So we call that tertiary. And what about the purple carbon right here? What do we call that? Primary, and the reason we call it primary is because it is attached to 1 other carbon. Cool. So now we know that this is only going to break in acid, and acid catalysts prefer what order for cleavage? Remember, they're a pain in the ass. Yes, 3, 1, 2. So between our tertiary option and our primary option, which of them is the acid going to choose? Tertiary, exactly. And so again, what we mean by choose is that the nucleophile will attack the tertiary side and we will break open towards the primary side. So I'm going to give you guys like 1 minute to think about the next 2 and let me know, or I'm going to let you work on that and I'm going to send you the attendance link. So do the thing.
How do you know where oxygen will go once it's broken?
Because whatever side you attack based on the acid or base catalyst, the oxygen just goes to the other side that it's attached to.
Oh, okay. Thank you.
You're welcome. And someone asked, does it matter from which side you start numbering? No, because the chain isn't going to change no matter how you number it. And essentially, we're not naming it, so the order doesn't really matter. We're just using an arbitrary numbering system to allow us to keep track of everything. Okay, so now that I've sent you that link, please fill it out at some point. Because, you know, whatever. I know it's super annoying, but... Alright, so the pink carbon is what? Primary, secondary, or tertiary? Secondary, cool. And the purple one is what? Yeah, exactly, secondary. So, which one will the acid choose? Either, exactly. It doesn't matter. There's no preference. Both sides are exactly equal. Cool. So for this third one, what do we think about the pink carbon? Excuse me. Secondary, exactly correct. And what about this purple one? Tertiary, awesome. So which side will we prefer to attack? Based on our acid rule? Tertiary, cool. So the nucleophile will come in and attack this carbon, and we will break open the chain, and the oxygen will go towards the secondary carbon. Awesome. You guys are killing it. Any questions based off of what we just did? Wow. Sorry, I make myself laugh. Someone said, wait, I'm waiting. Okay. Go for it. When I was doing this in person, it would be really great because every time I would finish a topic, I would like step away from the whiteboard and everyone at the same time would pick up their phones and take a picture and put it back down. And that's kind of what I imagine is happening with the screenshots. And someone asked me, you know what, let me just draw the final products for this just to show you guys because a couple people asked me that. And I'm not going to give you a specific nucleophile. I'll just write NU for nucleophile. So for number 1, I'm going to go ahead and number using green. And just because I can, I'm going to start numbering here because that's where the nucleophile attacked. So 1, 2, 3, 4, 5. So I'm going to start with a base of 5 carbons. 1, 2, 3, 4, 5. And I'm going to start numbering here just because I said so. 1, 2, 3, 4, and 5. And so the first thing we want is to put the oxygen. So the oxygen is going to be on carbon 5. And we know that it will become protonated, so it will become an OH. And on carbon 1, we have 2 methyl groups as our substituents. So let me draw that in. Excuse me, the screen is like bobbing all over the place. And then in addition to that, we have our nucleophile. And that is it. There are no other substituents from this one. Oh, and someone said you guys are frozen. Of course you are. Let's try and fix that, shall we? Cool. And let's record one more time. Okay. Can you guys see the screen now? Yay, nay? Not yet? Okay. Let's give it a minute. Yes? Okay, cool. All right. So for the second one, as we mentioned, it'll be exactly the same no matter which side you cut open. So let's just say we cut open this side. That means we will attack this side. No, I lied to you completely. I'm so sorry for that. That means we will attack this side. And it will open towards that side. And again, I'm just going to start counting on the side that the nucleophile attacked. So 1, 2, 3, 4, 5. We have a 5 carbon chain again. And because I'm lazy, we're just going to duplicate. Oh, just kidding. It doesn't want to be duplicated. That's fine. 1, 2, 3, 4, 5. All right. So on carbon 1, we are going to add a methyl group. And I'll label that carbon 1. And also, we attach our nucleophile. Right? And then we go down the chain. 1, 2, 3, 4, 5. On carbon 5, we have another methyl. And we also have our OH. So I'm going to draw in OH. Last but certainly not least, I'm going to start numbering again at the side that the nucleophile attacked. 1, 2, 3. We have a nice and easy 3 carbon chain. And we'll count that as 1, 2. Wow, I said nice and easy 3 carbon chain and I drew a 4 carbon chain. That's awesome. So on carbon number 1, we have 2 methyl groups. So bam and bam. And on carbon number 3, we have 1 methyl group. In addition to that, our nucleophile is attached to carbon 1. And our alcohol is attached to carbon 3. So, ta-da. Now, any questions while I leave this up for a second? You are very welcome. And then I think I answered all the questions in the chat, but if you already asked a question and I didn't answer it, feel free to re-ask it. Okay, so someone asked about the example number 2, and since there's no difference, both sides are secondary, you don't really have a preference, so you can attack either side and you will get the exact same answer. No difference. You guys are asking fantastic questions. The last thing we're going to talk about for ether cleavage is an example of an exam-like question. And it says, which of the following is least likely to cleave when added into a solution of acid? Right? So we already talked about... Sorry, that was bothering me. So we already talked about what we like in terms of primary, secondary, tertiary, allylic, benzylic. And so we're going to use that now. So we like tertiary the most, secondary, and then primary the least. And so here we have tertiary, 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 secondary, secondary, primary, secondary, primary, primary. So which of these is going to be the least stable, aka least favorable one? I got one person who answered it, but I want a couple more people. And just in case you guys can't see it, this is 1, 2, 3, 4, and 5. Okay, so a couple people have answered, and we're stuck between two options, which is, again, what I wanted to happen, so yay us. So you guys are stuck between 1 and 3, which is good. So 4 and 5 are automatically out because they're both tertiary, so goodbye. Number 2 is in the middle. It has 1 primary and 1 secondary, so that one's also out. So we're stuck between primary, primary versus secondary, secondary. The order is 3, 1, 2. However, this does not actually matter for that order. I am not entirely sure why, but when we're talking about most to least likely to cleave, we're actually just going to follow the order 3, 2, 1 because we're going to form a carbocation, and the most stable is going to be tertiary, then secondary, then primary. So we're not looking at which side the nucleophile wants to attack. We're just looking at stability. So between primary and secondary, which one would be more stable? Yes, so number 2 would definitely be more stable. Therefore, this will be our answer. And again, the reason why the primary side is the least likely to cleave is because we are going to form a carbocation, and it's going to be the least favorable because it will be the least stable one. That was a mouthful. You guys have blah, blah, blah. You guys have any questions or you want me to repeat it, please let me know. I'll be patiently waiting. Okay, so a couple people asked pretty much the same question. So the reason why this is going to be a different order than the order of reactivity is actually because we're not talking about where the nucleophile will attack. We're actually just talking about which one will make the most stable intermediate. So when we break this, one side is going to be left alone as an anion, or a carbocation, my bad. And so the carbocation is going to be most stable when it's tertiary, and then secondary, and then primary is the least stable. So if he asks you for which is the most likely to cleave, he wants you to do this order. But if he asks you which side it would attack, then we use the 3-1-2 order. So for sure, for these kind of questions, think about stability. For these kind of questions where we're actually breaking open the ring, think about acid and the order for acids. All right, so there's one more thing I wanted to cover today. So we're going to scroll on to the next page. And we'll talk more about epoxides on Wednesday. But I wanted to let you guys know, epoxides can be cleaved in what? What do you guys think? My people from Friday. Both. So it can be cleaved in acid and base. And you might have been, the answer might have been given away by this, but that's okay. So we already said that acids are a pain in the ass. So what is their order of reactivity? 3, 1, 2. Sweet. And so bases, listen up. Bases are actually just our plain old basic bitches sitting around drinking an iced coffee, chilling, right? So since they're so basic, they're not even going to be original. They're just going to follow the number line. So it'll go primary. Ooh, that's not a number. Primary, secondary, tertiary. So basic. So once again, pain in the butt because I don't want to get in trouble. And then bases are basic. Whatever. So I hope this helps. If nothing else, during the exam, you'll just hear me screaming in your head, basic bitches. So, you're welcome is what I'm trying to say. And then I'll go into examples next time, but I just wanted to give you this information. So, just to kind of recap everything we talked about today. Epoxides are... Actually, we're going to have fun. You guys can unmute or you can write in the chat, but I'm going to ask you guys some questions, and I want you to answer kind of as fast as you can. And I'll make this go out of the way. I think the screen is frozen. Okay, we're good. So, anything with a negative charge can be a what or a what? Nucleophile or a base. Awesome. So, the Williamson blank reaction makes what? What functional group? The Williamson synthesis. Ether. Awesome. And it's called the Williamson ether synthesis, which would have given it away. But so the intermolecular gives us what? Linear or cyclic ethers? Linear. Okay, so what about the intramolecular? Awesome. So inter is linear, intra is cyclic. So, what is the difference between the intermolecular and intramolecular when you talk about your reactants? And it can be just super basic. Yes, awesome. So the main idea, inter, leaving group, and nucleophile are on different carbon chains. Intra means that the leaving group and the nucleophile are on the same carbon chain. Awesome. You guys are killing it. Okay, so acids. What is the order of reactivity for acids? 3, 1, 2. Sweet. Okay, so what is the reactivity of bases? Awesome. Okay, so... Oh, here's a fun question. How many carbons apart do the leaving group and the nucleophile have to be in order to make an epoxide with the intramolecular Williamson ether synthesis? That one's kind of hard because I didn't say it explicitly. But think about it. And you can look at the example. Okay, we got a couple different answers, so let me go ahead and go back up to that reaction. So, they're actually going to have to be right next to each other. So, technically, you can think of it as 1 carbon apart. But what is this relationship if they are 1 carbon apart? Vicinal! Cool! Okay. What if they were on the same carbon? What is that called? Geminal. Sweet. Okay. So, what exactly is an epoxide? I know it was literally just on the screen, but what's an epoxide? Yay! A cyclic ether with 3 members. Awesome. And the last question for bonus points, right? Well, I can't actually give you bonus points, but in my heart, who is the... Someone said banana bonds. Yes, but that wasn't the question. Who is the mascot for Orgo 2? Bear! Yes. Okay, I'm sorry that was obnoxious, but I had to. So yes, Bear is our mascot from now on. And I'm glad you guys love him because I do too. And someone said, what do you mean by 3 members? So an epoxide has 2 carbons, as we see here, and 1 oxygen in the ring. So that is 3 members in the ring. So yeah, that's pretty much all I have for you guys. Bye!